All right, so I messed up when I posted things specifically to the White Day Classroom for 2017. My plan was to post question 3 and 6 and then videos for 3 and 6, and I posted 3 and 5. So, this question, number 5, is not one that you have to do, but I know that if you did take the time to do it, you're going to want to know what the answer is. So, here I am making another video. I think I'm talking to myself so much that I'm losing track of what I've said. But I want to go through this question. There are a couple things on this question that are beyond the scope of what we've done. But really, there's only one thing that's maybe kind of confusing to understand, and we can't relate it to what we've done. For the most part, I can connect this to things that we've done, and it actually isn't too bad. Especially the way it starts. So here's what we have. We have this particle that is two particles, P and Q. P, we have a position function. Anytime they want to talk about position, they're probably going to use the letter X to represent position. And then Q, they give us the velocity equation for that. They also tell us an initial velocity or initial position for Q. So question A, part A, wants to know when is the particle moving left. So here's the piece about velocity that you may have a little bit of understanding, especially from some science classes. Velocity, the sign will tell you the direction. So if you have a positive velocity, we think of moving it to the right. We think of like horizontal motion, right being positive, left being negative. Sometimes you'll have vertical motion where up is positive and down is negative. So when it wants to know when the particle is moving to the left, what it's actually saying is when does it have a negative velocity? So the first thing you want to do with this is you want to get a velocity equation. And this is a nice review of how you take the derivative of a natural log, because that's what x is. So a natural log, the derivative is du over u, the derivative of this over this. So the derivative of it is 2t minus 2 over the original t squared minus 2t plus 10. We want to factor. We can factor a 2 out of the top. We get t minus 1. The bottom actually won't factor. And I did try very quickly, but since this is not a calculator question, if I don't have a quick factoring, I'm not going to be able to do anything with it. So I'm going to focus all my energy on the top. So I know that the top will equal 0 when t is 1. So that kind of think of it as like a critical value when you do derivatives and talk about increasing versus decreasing. With velocity, that means where you have that stop or that hesitation, and then you may change direction. So you may go left or right once you get to that 0 velocity. So to determine, I kind of made a little number line here, so I'll explain what I wrote here. So I know 1's kind of my tipping point, my changing point. And then if I look prior to 1, so if I put like a half in here or 0 in here, I get a negative velocity. That tells me the direction is left. And then if I put a number bigger than 1 in, like 2 or 3, I get a positive velocity. It tells me it's moving right. Very similar to what we do with increasing and decreasing is the way you should connect it. So since it is a negative velocity before 1, then we would say that it's moving left from 0 to 1. We're only working with times that go from 0 to 8. So that's why I never even mentioned negative. You can't have negative time anyway. So it's moving to the left when the velocity is negative, and that's going to happen between 0 and 1. So for the grading, I think they did very similar that I did. They took the derivative. You get 1 point if you derive it, even if you have no idea what to do with the derivative. And then your last point is for that interval from 0 to 1. And there's lots of ways you could write it. You could just write it in words. Then part B wanted to know when are the two particles going to be traveling in the same direction. So you already know what's going on with this particle P, that it's moving left to start, and then at 1 it turns and starts going to the right. So then you do the same thing with B. They already gave you the velocity, so you don't need to derive this. You can go straight from this. This is factorable. It factors t minus 3, t minus 5. So there's two potential direction changes at 3 and at 5. So I made another number line. You could put them kind of close to each other so you can compare. From 0 to 3, I wanted to check what the sign of the velocity was, and then from 3 to 5, and then from 5 on. So from 0 to 3, if I pick any number like 1 or 2 and put it in here, I get a positive velocity, so it must start moving right. Then if I put 4 in, which is in the middle interval, I get a negative velocity, so it must turn around and start going left. And then if I put a number bigger than 5 in, like 6 or 7, I'm back to a positive velocity, so it changes again, and now it's going to the right. So if I compare these two, in the beginning, this one's going left, this one's going right. So we don't have anything happening right away. Once we get to 1, the first particle, P, is moving to the right. This one is still moving to the right. So it starts at 1, moving the same direction, and then it stops at 3, because at 3, now it's turned around and starts going left. But then it starts going right again at 5, and this one is still going to the right. So we actually have two intervals, from 1 to 3, and you don't need to actually include 1 and 3 because that's like a direction change. And then from 5 to 8. The reason I included 8 is because 8 is the end of the interval, and at that point, they're both going to the right. So I just wrote down these are my intervals, and then the reason is because they both have a positive velocity there. What did they do for scoring? They said if you essentially you set up intervals. So this is kind of only one interval with analysis. So if you only looked at like one part of it, I can see that's what must be what they're saying, because there's two intervals. You're 1 to 3 and 5 to 8. So if you only had one of those two intervals, you can get a point. If you never analyze, if you never talk about positive versus negative, then they're not going to give you anything. The 2 points come from one saying the two intervals and one saying I'm using these two velocities and comparing side by side. They actually did one on top of each other. Then for part C, it wanted to know the acceleration at 2. So that's the easiest part of this question. And then the second part is something that we didn't quite get into. So acceleration is the derivative of velocity. So the first thing I did was I derived velocity. And here's my work. 2t minus 8 is the derivative. It wants to know what happens when you put 2 in. So you put 2 in, you get -4. So that's the easiest part of the question. Then it wants to know if it's increasing or decreasing in its speed. That's going to come from comparing the velocity and the acceleration. And this is something for those of you taking BC next year, we're actually going to get into a lot more depth. The idea is if the velocity and acceleration have the same sign, it's going to be speeding up. You're actually like pushing it in that direction. If the signs are opposites, it's like kind of like they're butting heads and you're slowing down. So I compared the acceleration at 2 is 4, or excuse me, -4. The velocity at 2 is +3. Because those signs are different, we say the speed's decreasing. I don't expect at this point you guys to be comfortable with that. Now, part D, I do expect that you could do part D because part D is a fundamental theorem of calculus. Well, let me show you the grading for part C real quick. So part C, the grading was 2 points. The first point to me is very easy, taking the derivative and plugging 2 in. The second point is speed decreasing is more challenging. And then finally, part D wanted to know the position the first time it changes directions. Well, from my number line, I can tell the direction change happens at 3. So I want to set up an integral. If I integrate velocity, I get position. When I integrate, 3 is one of my boundaries because that's what I'm trying to figure out. I also want to use 5 as a boundary. And the reason I want to use 5 is it's what I know about. I know that when, not 5. I want to use 0 because that's what I know about, because I know at 0 I get 5. So that's that given information I'm going to use. So let me show you my work. So my integral goes from 0 to 3, again, what I know and what I need. I'm going to integrate velocity to get position. So when I integrate velocity, I get the position at the top boundary 3 minus the position of 0. This integrates by hand. When you take the actual AP test, you will be able to use a calculator. So if you have anything like that, you can go to Math 9 and save yourself a lot of time. You can end up getting 18 when you do that by hand or with a calculator. That is x of 3 minus x of 0. We know x of 0 is 5. That's that given information. So I'm going to add 5 to the other side. So the position at 3 is 23. So the way they scored that is they gave 1 point that you knew how to integrate it. So 1 point is that process of integration. 1 point is you knew how to use the initial condition. So you knew to use that when time is 0, your position is 5. And then your last point is for your answer. Now on the test that you're going to take, since you can use a calculator, they would not have you do the integration by hand, but they could have you set up integrals and show what that represents. So again, integrate velocity, you get position. So that is question 5. I apologize again for the mix-up. I do want you to score questions. I think it's so far I've given you 3, 4, and 6 from 2017, and I have those videos released. This one, again, is just a nice additional one if you have time. I don't want to put too much on your plate, but I would like you to look at the other ones from 2017 because I think they are very representative of what you'll see. Have a good day, good night, whenever you're watching this, and we will talk soon.